All right, well, we actually have kind of a neat connection to show you, but I don't want to say we have to get past this, but we have to figure out kind of this just pretty standard problem here. It's basically finding the slope, okay? But there's some language, and that's on purpose so that we can transition this to something kind of neat in a second. But for a moment, we're going to find the average rate of change, which quite frankly is just the slope between 2 points. The slope between 2 points is essentially the change in the y over the change in the x. Okay, but I want to use that notation where we sort of force ourselves to think about f of x2 and f of x1, even kind of like off to the side here. But understand what's happening. All I'm doing is finding the y value. I'm finding the y value, something that you've done in an algebra class. Obviously, you plug in. Okay, now it's supposed to be kind of easy, but I just want you to see what's happening here with numbers. To fill you in a little secret, soon we'll do this with some letters, and then it gets a little more interesting. So f of x2, in other words, the y value is 3. Yeah, is 6. And then we need to find the other y value. So, of course, we'll plug in 1. That actually comes out to be 0. So we got ourselves a couple y values, which according to good old algebra, all you have to do is subtract them to get that average rate. By the way, we're calling it an average rate kind of on purpose, because in a moment we'll switch this to another type of rate. So I got a little change in y over a little change in x, which is basically the slope of the secant. If you're saying, what do you mean slope of the secant? I'll show you. But it comes out to be 3 for a nice little average rate. Now that means that there's a line that goes from x equals 1 to x equals 3 that has a slope of 3. And that line is really nothing more than just a line that connects x equals 1 with x equals 3. You've seen this kind of line before. It's obviously straight, but it's called a secant. It's called a secant because it basically connects 2 points. Okay, and the 2 points that we connected were 3, 9 with 1, 0. Okay, now you should say, give me 10 of those to do. I'll get them all right. I won't give you 10, but there will be a couple of them. But the real reason we're doing this problem is so that we can transition to something pretty neat. Okay, it's called the instantaneous. It's called the instantaneous rate at x equals 3. I guess we're going to try to find it, so I should put the word find in front of it. But let's talk about this new idea here, this instantaneous rate. Now, again, the rate that you found was the average. It was the average because it was between 2 points. You kind of take your beginning, you take your end, and you average it. But now I don't have an animation for this, although I will show you a little video of something else. But I want you to kind of pretend that this point right here is dragging itself closer and closer to x equals 3. And so imagine that this line, the secant line, is also connecting and dragging itself closer and closer to x equals 3. And in a sense, we would be able to still have a sloped line. Now, don't overthink this and think that it's like vertical. All I'm trying to show you is that this line is going to, because the points get closer, is going to drag up closer to x equals 3. And we would be able to have that slope. Now, that slope is a different type of line. It's called a tangent line. It's called a tangent line. And so we actually call this the slope of a tangent instead of a slope of a secant. Now, you've seen tangent lines in geometry, maybe, if you remember that. But just recall with me that a tangent line only touches at one point. And here lies a little bit of a dilemma. How are you going to find the slope if you just have one point? Okay, I thought slope was the change basically between 2 points. Just think about that with me again. We have a little dilemma. We're trying to find the slope at one point because this tangent line, by definition, is only touching at one point. So what are we going to do? Because the definition of slope has to be the change in 2 points. What we're going to do is we're going to pretend. Pretending is fun. Hopefully you did it and still don't mind doing it. We're going to do a little math pretend. We're going to pretend that there's another point that's really close to x equals 3. Now, it's kind of arbitrary, but we're going to call it 3 plus h. We're going to call it 3 plus h. And just so you know, we're not worried about the y value. We'll figure that out. But we're going to pretend that there's an x value really close to 3. We'll call it 3 plus h. Now, if you're saying, what's h? Well, it's going to end up being like a small value. In fact, I'll tell you a little secret. It's going to approach 0. H is going to be a value that approaches 0. Sound a little bit like a limit. Okay, we'll get there. But for now, let's find the slope. Okay, now, I didn't need to write that yet. Let's find the slope. But to find the slope, we need some y values. We need f of x2 and f of x1. So what we're going to do is we're going to plug in our pretend point. So we get a y value. And we're also going to plug in our actual point. Now, it's an important part of the lesson to start paying. I hope you're still paying attention, but continue to pay attention because we're going to plug into this equation. Sometimes kids are like, where are you plugging in? We're still using the same equation. If you need to somehow highlight it, please highlight it. We're going to plug in 3 plus h, and I don't want you to just think that this is just kind of random stuff. In other words, the reason I'm squaring it is because that's what the equation says to do. It's x squared. And the reason I'm subtracting it is because, again, that's what the equation says to do. So I'm plugging in 3 plus h. Now, it's probably not a surprise to you that that's not going to come out to be a number. That's not going to come out to be a number. It's going to come out to be an expression. But it's still like the y value. It's like the pretend y value. Now, do some 3 plus h squared carefully, please. Do not do this. If you've had me before, I've said that's a math teacher's nightmare. Maybe I already said it this year. That's a math teacher's nightmare. Do not square 3 and h, but you can square 3 and get 9. You can multiply these together and double it to get 6h, and you can square h to get h squared. And then I hope you're going to subtract 3 and subtract h. Probably not a bad idea to write that stuff down, but ultimately we just want to get the simplified version of this. It looks like we're going to end up with a 6, a 5h, and an h squared. Try not to just be copying. Make sure you're thinking. We're finding the slope at a point. But the definition of slope requires 2 points. So we made up a pretend point. The reason we made up a pretend point is so we could get a pretend y value. Now we're going to get a real y value when we plug in 3. We already did it. Okay, it's going to come out to still be 6. If you want to show it again, you can, but when you plug in 3, you get 6 again. Now I have some numbers that I can subtract to find the slope. Technically, I'm going to be finding the instant slope. Technically, I'm finding the instant slope. But for a moment, it kind of feels like I'm still subtracting the y values. Now, here's the first y value. It was my output from my pretend x value. So there's my first y value. There's my second y value. The definition of slope says that you always subtract them. And then you divide it by, of course, the change in x. Now the change in x would be my pretend x value minus my real, check that, my pretend x value, minus my real x value. Anything you see here that you have a question on, I just want to give you a chance to pause. We're going to simplify it, but do you understand where all the numbers came from? This is kind of interesting. The slope, has h in it. Well, keep watching. This isn't that hard. All you're seeing me do is just some basic combine like terms, right? Just combine like terms. It looks like the 6's cancel. It looks like the 3's cancel. This is interesting. I get a slope that has an h in it. Keep watching. We're still going to just do some algebra. Make sure that you're good with the heart method. It would definitely be the call here. You're going to take h and you're going to start to cancel it. This is interesting. We get a slope that has an h in it. What's up with this h thing? Okay, it was kind of used to pretend that we had a point really close to 3. But as I mentioned at the beginning, we actually want h to approach 0 because technically we just want to have 1 point at 3. So how do we make h approach 0? Well, you pull out a little limit. My voice is kind of cracking. There was a cross-country race yesterday, and Mrs. Krause said, "Was that you yelling down there?" So just kind of, I can't run, but at least I can yell at the kids to try to run. Run! All right, we're going to pull out a little limit. As h approaches 0. As h approaches 0. Now, it depends on where you're at right now. I realize you're all unique. You could be somewhere else maybe, but the best you can, try to be here for a moment. This is neat stuff. We are using a limit. To take a make-believe point and actually essentially make that point fuse together, become just 1 point. We're using a limit so that we can make it be 1 point. You say, why do you want it to be 1 point? That's what it means to be instantaneous. That's what it means to be a tangent. And it's actually really easy to do. Make sure you don't make this limit too hard. Plug in 0. You end up with an actual number. You end up with an actual slope. And I'm sure there's not one of you that would say that this line doesn't have slope. Sure, it has slope. I mean, there it is. Even though it's just a sketch on the board, it's got a slope of 5. Okay, and that would be the slope at x equals 3. That would be the slope of the tangent at x equals 3. Now, you might not know it now, but I'll fill you in a little secret. That's like one of the main concepts in calculus. It's such a main concept that we will spend a good part of October, November, and December talking about it. So what just happened today, finding the slope of a tangent, you'll begin to realize is, again, a big idea in calculus. And it really is brought to you by limits. It's brought to you by limits. Now, there was some fancy stuff we did right here, and you'll have to do it again, but you're going to find out that every time you do it, that you get the cancellation that you witnessed right here. You get numbers canceling in the denominator. You get numbers canceling in the numerator. You get h's canceling. And so we come up with a more refined formula that students are able to kind of quickly go to, basically to make their life a lot easier. And this is a formula for the slope of a tangent at x equals a. X equals a. And it looks like this. Now, again, I could have maybe just threw this up on the board and we could have tried to use it, but most of you probably like, what is that? So I hope you have a little more of an appreciation that, first of all, it's a limit because we want to have 1 point. In other words, we want our pretend point to become 1 point. Now, you'll still have to pretend. You'll still always make this a plus h point. You'll still subtract the y values. So it's f of a plus h minus f of a. But in the denominator, we can kind of simplify it a little more quickly and realize that we're always going to end up with some cancellation to just be h. So the denominator is just h. And don't worry, if you're like, oh, that's going to give you a 0 in the denominator. It's not going to give you a 0 in the denominator because eventually you'll also cancel that h out. But again, we'll do it. We'll show you. We'll do some problems and you'll see why. Let me show you something that will help you understand this idea of a tangent line. There's lots of things on YouTube, maybe that are better, maybe that are worse, but what you're going to see here is a tangent line in red change its slope based on its position on this function. So tangent lines can vary. Nobody told me that I'm the only one watching this. Let's try this again. Here's a function. Okay, and then there's a tangent line. It's in red. And you're just going to see its slope change as it moves along the function. Now, the slope of that tangent line is really steep right there. It's not so steep right there. Right there, it's equal to 0, 0. And even in the middle right there, it's negative. So the slope of that line keeps changing as basically a point. It's kind of like there's a point that's moving along here, gets to different positions. So the main takeaway, I want you to realize that you can have many different tangent lines representing many different slopes. Is it me or is the thing like speeding up? Yeah, it's, whoa. The cool thing about the calculus that's in front of us for October, November, even into December, is that you're going to take functions that you've studied in algebra and you're going to analyze them now with calculus. What's that mean? It means this. Okay, it's the big idea. It means analyzing for the slope of a function. And when I say that, that implies the instant slope. Okay, the slope of a function at a given point is special. It has connections to physics. It has connections to money, all of which I'll be showing you. But it's all going to be about the slope. That's the little secret that, again, is kind of in front of us. Okay, now we have a little more to do with this. We'll do it tomorrow, but this is going to be a quicker one. So just so you are kind of ready for a faster turnaround, after tomorrow, it'll be time to fire up the next assignment, which you'll get to work on Friday, which is why Tuesday is kind of like a wrap-up day, and then Wednesday being a review for a test that's Thursday. Okay, so it'll go a little more quickly here in these next 5 school days.
I was just going to ask you next time.
Tuesday. It'll be due Tuesday. All right.